Greetings everyone, I am Karan Ahuja, a fourth year PhD student at the Human Computer Interaction Institute of Carnegie Mellon University. Today, I'm going to talk to you about my work on BodySLAM, Opportunistic User Digitization in Multi-User Augmented and Virtual Reality Experiences. This work was done with my collaborators Mayank Goyal and Chris Harrison at CMU. When we talk about tracking in extended reality systems today, we often think about headsets with handheld controllers for input, such as the HTC Vive, or controllerless hand tracking as featured in the Oculus Quest in virtual reality, or the Microsoft HoloLens in mixed reality. Now, there are many other facets, such as the user's body pose, facial expression, skin tone, and apparel, that would be extremely valuable to digitize. However, to get this holistic view of the user, we require costly instrumentation of the environment with sensors such as depth or view spectrum cameras or full-blown motion tracking systems such as Vicon and OptiTrack. The other alternative is to instrument the user with multiple sensors as can be seen on the left, or wearable mocap suits as can be seen on the right. Researchers have also used non-visual sensing modalities such as RF reflection and capacitive sensing. In this work, we take advantage of an emerging use case, co-located multi-user AR/VR experiences. Although nascent, the application space for these paradigms are quite diverse, ranging from multiplayer games, as we can see here, to medicine and healthcare, and also to AR augmented collaborative spaces. One commonality in all these scenarios is that the users look and face each other while immersed in these experiences. This opens the possibility for the opportunistic capture of other users. For example, in this scene, two users, A and B, face one another, perhaps playing a mobile AR game where full body tracking would be valuable for expressive input. Unfortunately, neither phone is able to see and thus digitize its owner's body. However, users B phone can see user A and users A phone can see user B through its rear-facing camera. BodySLAM uses this view to capture and digitize the body, hands, and mouth of user A and share the data visualized as A- back to user A. User A does the same for user B, providing ad hoc full body tracking B- without having to instrument either the user or environment. This is the core idea behind BodySLAM. Let's walk through an example to see how this works. Here, you can see users wearing mixed reality headsets playing an augmented reality ball game. These are the respective views from the HMDs of each user. As you can notice, users can look around and see each other. To understand what is happening, let's zoom into the view from user C. The first step is to identify and localize other users in the view. That includes IDing them via their Aruco tags. For example, here person C sees person B. Not only that, person C can also estimate the body key points of person B and then relay this information back to him, thus giving him his digitized body for interaction purposes. Now, taking all these different perspectives together, this is what our system looks like in action. Furthermore, in many cases, a user's body is seen by more than one person. In such cases, 3D pose can be estimated via stereo reconstruction as seen here. Also, even though I currently talked about body pose, in an analogous manner, hand and mouth pose can also be estimated. From this pose information, gestures can also be inferred. For this, we make use of unidirection vectors between pose key points as scale invariant features and a multi-layer perceptron as the learning algorithm. In this manner, we classify the hands into 5 gestures: OK, thumbs up, high five, peace sign, and fist. Similarly, we use the mouth key points to classify them into 3 mouth states, namely mouth open, smile, and neutral. Let's go back to our multi-user scenario and look at some of the other capabilities of BodySLAM. As we just saw, users can't see themselves, and thus everybody is given their pose by someone else. What you see here is the top-down view of this scenario. The placements of the video frames here are not arbitrary, they represent the actual positions of these users. This pairwise information of which user is viewing whom is used to create a directional graph with spatial information, allowing BodySLAM to compute a global scene in real-world coordinates. Note that users that see no one, like user E, can still be added to this graph if at least one person sees them. Likewise, a user that is not seen by anyone, such as user A, can also be added to the graph if they see at least one person. Now, taken together, we have the global scene topology, the position of different participants, and also their pose. Another thing I would like to add here is that we created 3 exemplary prototypes for BodySLAM to cover different AR/VR modalities. In prior slides, you have seen the mobile and head-worn AR in play. Analogously, BodySLAM can digitize bodies in VR as well, as shown here. I will now walk you through over the various studies we conducted to test the efficacy of BodySLAM. For all these studies, we used the head-worn AR form factor. For our static activity, we emulated a meeting context in which the participants met face-to-face, reflected in the one-on-one condition, or in a group of 5 to mimic a conference room setting. In these scenarios, the participants were asked to perform 10 body gestures, 5 hand gestures, and 3 mouth states. BodySLAM ran live and all the participants saw their live pose and gesture estimation in an AR overlay which they self-judged. The gesture classification accuracy of BodySLAM can be seen here. Body gestures had a mean classification accuracy of roughly 94%. That for hand and mouth states were 88 and 91% respectively. Upon further inspection, we noticed that body pose accuracy increases as the distance between the participants increases. This can be attributed to the fact that at larger distances, the whole body is visible. However, hand and mouth state recognition degrades as they benefit from being closer in order to provide sufficient camera resolution to resolve fine details. Now, to test the efficacy of BodySLAM in real-world scenarios, we ran a dynamic activity study. For this, the participants played a ball game for 5 minutes, during which they were allowed to move freely around the room to create a natural interaction environment. This introduced challenges such as motion blur, occlusion, and misalignment. To evaluate the performance of BodySLAM, we randomly subsampled a set of frames from the dynamic activity sessions and asked expert annotators to evaluate body, hand, and mouth key points, which they found to have a mean accuracy of 96, 93, and 61% respectively. For further details on this, please refer to the full paper PDF. Apart from the body digitization accuracy, it is also essential to evaluate how many times are people registered in our global scene topology. In other words, at any given time, what is the percentage of total users captured by our system? The overall user registration accuracy of our system is roughly 95%. Across the dynamic and static activities, we noticed that the group activities had a lower registration rate due to occlusion of the Aruko tag and motion blur introduced due to head rotation and translation. To study the effects of user registration across larger groups, we also ran software simulation in different sized rooms with different body orientations such as random and common focal point to simulate scenarios such as conferences and stadiums. We found that performance improves as the number of users in a space grows. It is important to note that while our system has promising results, there are several key limitations that need to be addressed before our system is ready for wide-scale deployment. The first is the heavy computational requirement of running computer vision modules such as pose detection and Aruko code registration, which can introduce noticeable lag, which is currently 150 milliseconds on an average for users. Fortunately, smartphone manufacturers are increasingly including hardware-accelerated deep learning capabilities, which should improve performance in the coming years. We also note that BodySLAM is limited by the field of view of the camera and occlusion in the environment. Thankfully, ultra-wide-angle cameras, such as the 120-degree one on the iPhone 11, are now becoming prevalent in smartphones, which can increase the body registration accuracy of users. We also acknowledge that our use of Aruko for person identification is inelegant and requires instrumentation of headsets or smartphones. In future, we hope to move towards markerless techniques for IDing. This wraps up my presentation. Thanks for watching. For any questions, please feel free to reach me on the email ID shown on my slide.